We're now going to make a few observations about accessible states. First of all, the accessible number of accessible states we show with letter omega, as you remember. So what determines these accessible states? It is determined by some macroscopic parameter y. Omega, the number of accessible states, is a function of some macroscopic parameter y. So the set of accessible states are determined by specifying the constraints on the system as determined by the value of some macroscopic parameter y. For example, what I said here we can demonstrate for ideal gas that is confined in volume. So the constraint on the system here is volume. So I have an ideal gas that is initially trapped in an initial volume V initial, and therefore the number of accessible states for this scenario will be omega is a function of volume, which is V initial. So in the first configuration, when the volume is constrained to be V initial, I have the number of accessible states omega initial. So constraint on the system is V must be equal to V initial. So this is what the macroscopic parameter y that I'm talking about. So by specifying the value of this macroscopic parameter y, which is volume in this case, we determine the number of accessible states to the system. If I remove this partition and let the gas expand to fill the full volume, final volume V final, so here I'm going to have, in this scenario, omega is determined by the new constraint on the system V final. It will be the final number of accessible states in this system. And I have V final greater than V initial, and omega final is going to be greater than omega initial. So if V final is greater than or equal to V initial, omega final will be greater or equal to omega initial. So this number of accessible states is completely determined by this macroscopic parameter y. The value of y in this case is V, and the value is V initial or V final, and that determines the number of accessible states on the system. Now the second important thing I would like to note here is something we talked about before. This is the postulate of equal a priori probabilities. So that is to say, at equilibrium we must have the same probability for all accessible states. All accessible states are equally probable. Okay, So what does that mean for this example? So if you pick one accessible state here, the probability of one accessible state in this scenario would be probability of one accessible state, P1, would be 1 over omega initial. Probability of one or two accessible states, so P1 or two accessible states would be 2 over omega initial. Because remember, if it's either or configuration, we have to add the probability. So probability of having accessible state 1, either 1 or 2, then we add the two probabilities, we will get 2 over omega initial for this scenario. And similarly for the final volume, probability of having the one accessible state is going to be given by 1 omega final. Probability of having the first or the second accessible states will be 2 over omega final. If you want to know probability of having the first accessible state or second or third all the way up to the number of accessible states, the final omega final, you will have omega final over omega final, which is 1. That is our normalization condition. For statistical purposes, if we are studying these probabilities, when you form a statistical ensemble of all such systems, they must be subject to the same set of constraints. So remember, in statistical ensembles, we must have similar systems. Therefore, we must have the same constraints applied to those systems in the statistical ensemble. Okay, so this is another important point. In a statistical ensemble of systems, all such systems are subject to the same set of constraints. So remember our definition of probability. Probability of having an outcome R was defined as the number of systems in the ensemble that display outcome R divided by the total number of systems in the ensemble, as the number of systems in the ensemble goes to infinity. So in order to use this definition of probability, we must have the same set of constraints. So for the first system, the volume must be equal to V initial. Second system, volume must be equal to V initial. All the way up to n systems, volume must be V initial. So if we're studying the probabilities of these accessible states. And similarly, in the case of the second part, so this is part A, part B, in the final volume configuration, first system must have V final volume, second system must have V final volume, and similarly the nth system must have its volume equal to V final. We need the same set of constraints applied to all the systems, similar systems in the ensemble, in order to study the probabilities of outcomes. Okay. So when we have a constraint being removed, immediately after the removal, the system still can be found with equal probability in each one of its initial states. Okay, so when the constraint is removed, we will have immediately after the removal, the system can still be found with equal probability in each one of its initial states, initial accessible states. Okay, so immediately after the removal of this partition for this example, so here I have a partition and I'm removing the partition. So let's say that at t is equal to 0, the partition is removed. So if you ask me, at t is equal to 0 minus, the system was at equilibrium. Probability of one accessible state was 1 over omega initial. At t is equal to 0 plus, right after the removal of this partition, the probability will still be 1 over omega initial. So we have to wait for the system to evolve and the probabilities will change in time. So what can happen after the removal of the constraint is we have two possible outcomes. If the final number of accessible states is equal to the initial number of accessible states, so if we have this scenario, the removal of the constraint will have no effect. And on the other hand, if we have the final number of accessible states, omega final, greater than omega initial, then what we'll have at t is equal to 0 plus and t is equal to 0 minus, the initial probability for one accessible state or for each accessible state is 1 over omega initial for each accessible state, and then we will have omega final minus omega initial states will have 0 probability of occupancy. This is what will happen initially. And however, the probabilities will become time dependent. The system is going to evolve until the final equilibrium is reached. You're going to have P final is equal to 1 over omega final for each accessible state. So we're going to see in this case at t equals to 0 minus and 0 plus, the probability of one accessible state is 1 over omega initial. For t much greater than 0, the probability of having one accessible state will be 1 over omega final. This is going to be corresponding to the final equilibrium situation. Now, regarding these number of accessible states, I would like to make a quick calculation in order to have a more concrete answer for the number of accessible states. So first of all, I have an isolated system for this ideal gas that is inside the container. The total energy of the gas, initial total energy and final total energy, will be the same. However, the final volume will be greater than the initial volume VI. and I'm going to call V0 volume occupied by a single molecule. And in kinetic theory, remember, we have this volume negligible. So we're treating all molecules as point-like particles. Therefore, this is going to be a rather small number. So for part A, when I have the molecules trapped in the initial volume V initial, so this is V is equal to V initial constraint, and I will calculate the number of accessible states that is determined by this volume. So omega initial is what I'm after. So how many accessible states do I have? So let me ask this question. How many accessible states for one molecule in volume V initial? So how many accessible states do we have? Well, so you're going to have the volume of the single molecule is V0, and there will be how many compartments this molecule can go into. It's going to be V initial divided by V0 different locations. So we're going to have V initial divided by V0 accessible states for one molecule. Now I ask a similar question. How many accessible states do we have? How many accessible states for two molecules in volume V initial? The answer is for one molecule we had V initial over V0. So first molecule, you should say I have V initial divided by V0 states. And for second molecule, then since I have already occupied a volume V0, V initial minus V0 divided by V0 states. But since this V0 is negligible, basically I can neglect this, and for two molecules I will have the joint probability. The first molecule and the second molecule are both inside, so both 1 and 2 first and second molecules inside, I will have the total number of accessible states V initial over V0 multiplied by V initial over V0, V initial divided by V0 square accessible states. And I can basically generalize this discussion for n molecules. For n molecules, we will have V initial divided by V0 to the power n accessible states. Because for the third molecule, you would say V initial minus 2V0 over V0, but then you would say 2V0 is much less than V initial. So that's approximately V initial over V0. So for all of these molecules, since V0 is negligibly small, we take it to be actually almost zero in the kinetic theory. It's a point-like particle. V0 very small. Why? Because ideal gas point-like particles, right? So we can always neglect the volume. So therefore, for n molecules, in volume V initial, we're going to have the number of accessible states omega initial is equal to V initial divided by the volume occupied by one molecule to the power n. Now I can say that similarly, now I considered n molecules, the same story for n molecules in volume V final. I will have the number of accessible states V final divided by V0 to the power m using the same arguments. So if you consider omega final over omega initial, the relative the ratio of the accessible states, V final over V0 to the power m, V0 over V initial to the power n. This is V final over V initial to the power n. So omega final is omega initial times V final over V initial to the power n. So this is how the number of accessible states is changing with volume. Now, n is huge, Avogadro's number, of the order of Avogadro's number. It's a very big number. So even if you have V final slightly larger, what will happen is omega final will be much greater than omega initial because of this huge factor you have in the power. N is a very big number. Okay, so then I ask myself, what is the probability of recovery of the equilibrium situation? So only the initial accessible states will be occupied. No accessible states that have been created by increasing the volume are occupied. So let me find this probability, or in other words, what is the probability of recovery? Okay, so the probability of recovery at equilibrium I'm trying to find the probability that I have only the accessible states occupied. So for all states, since I have the same probability, 1 over omega final plus 1 over omega final, one accessible state or second accessible state or third accessible state, I'm only considering the accessible states omega initial states. So I will have the probability of recovery to be omega initial divided by omega final, so that omega final minus omega initial states not occupied. That is basically going back to the initial condition. What is this probability? The probability of recovery. It is V initial divided by V final to the power n, because omega initial is V initial over V0 to n, omega final is V final over V0 to n. Their ratio is V initial over V final to the power n. And what kind of a number is this? Again, n is Avogadro's number, of the order of Avogadro's number. It's very big. So, and you have V final greater than V initial, then the probability of recovery is going to be much, much, much less than 1. So it is very unlikely that the initial equilibrium situation will be recovered in the final equilibrium of the system. So this is basically giving us an important clue about irreversibility. So when we have the number of accessible states in the final configuration much greater than the number of accessible states in the initial configuration, the probability of recovery pi omega I over omega f, all so that all molecules will be in the initial volume Vi after the removal of the partition. So after obtaining the equilibrium, the final equilibrium situation, I'm asking what is the probability that all the molecules will end up in the initial volume. This is going to be very small. Okay. So at final equilibrium, we have to wait for a large fluctuation, waiting for this rare large fluctuation because its probability is very, very low, and reimposing the constraint, that is reinstalling the partition. Basically, I'm talking about a recovery of the original configuration is very unlikely. Okay, so this is an important conclusion. And in general, what process do we call reversible and what irreversible? So this is the general definition of irreversibility. If the final number of accessible states is greater than the initial number of accessible states, the process is irreversible. So this is an important conclusion we have. If the process is increasing the number of accessible states, it is irreversible. And omega final will be greater than omega initial if the approach to equilibrium, approach to final equilibrium, increases randomness and disorder. Okay, so in this scenario that we have, because the molecules have a very ordered configuration when the partition is removed, they have to uniformly distribute in the final volume to have the most random possible configuration, disordered configuration, and this results in an increase in the number of accessible states, which in turn implies the process is irreversible. Okay, so let's recap what we said here. The number of accessible states is a function of constraints on the system, which are experienced by the value of some macroscopic parameter y. When the system reaches equilibrium, all accessible states have equal probability, the postulate of equal a priori probabilities. If we want to calculate probabilities of certain outcomes in an experiment that we perform on the system, we have to form a statistical ensemble, and if there is a constraint on the system, the same constraint must be applied to all similar systems in the ensemble. Immediately after the removal of the constraint, the probability of having an accessible state is the same, 1 over omega initial. However, the system will evolve if the omega final is greater than omega initial until it reaches its final configuration where each accessible state will have a final probability 1 over omega final. So between for t greater than 0 plus, we have the probability of each accessible state is time dependent, and as t much greater than the relaxation time, tau r, the probability will not be time dependent anymore. It will saturate and each accessible state will have the same probability 1 over omega final. We have shown this for ideal gas confined in a volume. The constraint was that the volume is fixed to be Vi, where we have at equilibrium 1 over omega I probability for each accessible state. When the partition is removed, a new constraint is installed. Final volume is the V final is the volume of the system, and that means at equilibrium we will have probability 1 over omega final for each accessible state. When the partition is removed, as soon as the partition is removed, immediately after, the probability is still the same, 1 over omega initial for each accessible state, and omega final minus omega initial accessible states are not occupied, but as t goes to infinity, t is much greater than the recovery time, we will have the equilibrium probability 1 over omega final. And we calculated the number of accessible states for this scenario. For one molecule, we have volume V0, V initial over V0, different locations, different compartments for the first molecule to put. For the second molecule, so we want to have both first and second molecule inside. V initial over V0 states for the first molecule. For the second molecule, since we have already the first one inside, the total volume has decreased. Available volume for the second molecule has decreased. V initial minus V0, and we have this divided by V0 number of compartments available for the second molecule, but because V0 is very small, it's a point-like particle, we can neglect it, so V initial over V0 is also the number of accessible states for second molecule. So both first and second, it's the joint probability we have V initial over V0 square accessible states, and remember that these are statistically independent. For n molecules, we have V initial over V0 to capital N accessible states. So looking at the initial number of accessible states and final number of accessible states, V initial over V0 to N and V final over V0 to N, I realize that if the volume is even slightly larger than the initial volume V initial, since we have such a huge power, Avogadro's of the order of Avogadro's number, the number of accessible states is increasing immensely. So at this point, when we reach equilibrium, the final equilibrium, I ask myself, what is the probability of recovery? What is the probability of having all the molecules in the initial volume? So for each accessible state, each configuration where I have all the molecules in the initial volume, I have 1 over omega final probability, and so first configuration or second configuration, blah blah blah, omega I possible configurations to have all molecules in the initial volume. The probability becomes omega I over omega F. So it is V initial over Vf to the power n, which is very small because n is a large number, and V final is greater than V initial. This is V initial over V final is less than 1, and to the power n it becomes much less than 1. So the probability of recovery, the probability of having all molecules in the initial volume is negligibly small. Therefore, the process is irreversible. Well, in general, If omega final is omega greater than omega initial, if the number of states, accessible states is increasing, the randomness is increasing, the disorder is increasing in the system, the process is irreversible.